So let's go in the heart of optimization with one or several variables. The thing we're going to look for now is really to precisely characterize the local extreme values for a scalar function. Okay, so you may have already seen me draw the next drawings that we're going to do. All the ideas in 1 or 2 or 3 sketches, okay, which answer the questions what is a local minimum or a local maximum and what's happening there, and then we can get some characterization. If you remember, we're going to have order 1 conditions and order 2 conditions. Okay, so let's do that. What is a minimum or a maximum value? A local one, at least. A local minimum or a local maximum is a place where locally that's going to be a local maximum. All the values of your function are below that value, okay? And same thing for a local minimum. Locally, if you look around, that would be one local max, that would correspond to one local minimum. Locally, this point is below all the surrounding values of your function. Okay, so that's the characterization of your minimum or maximum. F of x star, in the case of a maximum, that would be greater or equal to f of x for x in a small neighborhood of x star, so small interval or a small ball, whatever the space you're in, located around your point x star. And same thing when we put the looking at a minimum x star, but the minimum one, that would be smaller or equal to f of x for all x in a small neighborhood around this one, okay, around x star. As long as locally it's something that looks like this is going to be a characterization of minimum or a maximum. Okay, so that's for your continuous function. Now let's assume that your function is one-time differentiable. What does it mean when you've got a local max? And what does it mean when you've got a local min? Okay, so in case of a maximum, if that's the highest value, it means that your function was increasing, reaches the maximum, and it's decreasing. Case of a local minimum, it's decreasing, reaches the minimum value, and then it's increasing again. But you know that we can translate the monotonicity of your function as a sign of the first order derivative. So that means that your first order derivative is going to be positive here, it's going to be negative here. So if your first order derivative is continuous, that means that your first order derivative is cancelling here, because it goes from positive values to negative values. Okay, same idea on the local minimum. Your function is decreasing, so the first order derivative is smaller than 0. On the side of your minimum, it has to grow again, so your first order derivative is greater than 0. It goes from negative values to positive values. It means that at that point, f prime is equal to 0. So we've got a great characterization. That's order 1 condition. We need to have a point where the first derivative has to be equal to 0. So the first thing we have is that x star is a local optimum. We need that f prime of x star is equal to 0. Okay? And be careful, you probably remember that. That's only a one-sided implication. It's not an equivalent, okay? Why is it not an equivalent? Because we could have places where your function has a first derivative that is cancelling. Typical example like this. Your function, it's a typical example, f of x is equal to x3, so that would be 0. That would be 0. At x3, you get f prime of x3, x2. So at 0, it's equal to 0. That's what is going to be called a critical point, but it does not correspond to minimum or maximum, because you see your function is strictly increasing on both sides. So again, we do insist that this is really a one-sided implication. So necessary condition of optimal value, we need that the first derivative is cancelling. That's a critical point. That's what is called a stationary point or a critical point. Okay, but now we see that it's the same thing that is happening in case of a minimum or a maximum, or in case where we don't even have one local optimum. The first derivative is cancelling. So how can we discriminate? Again, we're going to interpret the changes in the first derivative sign in terms of sign for the second derivative. So here, first derivative is positive, 0, negative. It means that your f prime of x in that area, is in that interval, is decreasing. So if f prime is decreasing, that means that f second is positive. Sorry, f second is negative. Of course, f second is negative. All right. And in the case of a minimum value, it's the same kind of idea. F prime is negative here, then it's equal to 0, and then it's positive. So f prime is increasing. So f second is greater than 0. Okay. And here, your function, here we've got that our third derivative is also equal to 0 in the second, we've got that f second, sorry, the second derivative is equal to 6x, and it's also equal to 0. So we don't have any specific sign for this one. And actually, f second would be negative here and positive here. Okay, so we get a change in the convexity of the function. So you probably also remember that we can characterize the convexity, what we just talked about before, in terms of the sign of the second derivative. We get that f is convex. That's equivalent, so f is convex, it's looking like this, to f second positive. And f is concave, or concave, convex down. Some people say that it's equivalent to f second of x smaller than 0. Okay, so this is, well, 3 drawings, a bit more than 2, 1, 2, and 3 drawings that really, if it's probably becoming something that you are very used to by now, but really know how to redo this reasoning, because all the ideas are here, okay? And we are just going to extend these ideas to more than one variable. Okay, so that's going to be the next section, the next theorem.